chain of events, cause and effect. We analyze what went right and what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is supported by you, our listeners. If you'd like to support the show, you can by becoming a premium supporter. Premium support is available via Patreon and now through the Apple Podcasts channel subscription. Premium supporters have access to early release, high-quality, ad-free episodes as well as bonus material from all of our shows, not available anywhere else. We're edging closer to our monthly goal to go advertising free across the network, but we can only do that with your help. Causality is also a Podcasting 2.0 enhanced show, and with the right podcast player, you can also stream Satoshis as you listen, at whatever rate you prefer, giving you complete control. The choice is yours. Visit engineered.network/causality to learn how you can help this show to continue to be made. Thank you. Florida International University. On the 5th of September 2013, the DOT notified the Florida International University, that's FIU, that it had been selected to receive an $11.4 million US grant that included funds for a new pedestrian bridge, and with additional funding, the bridge would cost a total of $14.2 million US dollars. The grant came from the Transportation Investment Generating Economic Recovery, or TIGER, and Transportation Alternatives Program, TAP, via the U.S. Department of Transportation, DOT, and with coordination from the Florida DOT, or FDOT, and the Federal Highway Administration, FHWA. That's a lot of acronyms. In mid-2014, the FIU released the design criteria for a new pedestrian bridge as part of their University City Prosperity Project that had been prepared by T.Y. Lin under contract. The winning proposal was from a joint venture between Manila Construction Management, MCM, though later renamed Magnum Construction Management as the prime contractor or constructor, and FIG Bridge Engineers Incorporated as the bridge designer. Further to this, FIG entered into an agreement with Louis Berger to perform an independent peer review of the bridge plans as required by law. There was a professional services agreement with Bolton Perez and Associates Consulting Engineers, or just Bolton Perez for short, to provide administration, monitoring, and inspection services for the bridge during its construction. The bridge was to be located on the western side of the intersection of Southwest 8th Street and 109th Avenue to allow safe student transit between a rapidly developing housing accommodation across the road, predominantly used for students attending the FIU, across an 8-lane highway that experienced an average of 60,000 vehicles each year. The architectural vision from the design criteria included, and I quote, "A design that will promote its own use is inherently connected to how well it ties into the context of the site, how intriguing it appears from afar, the experience of using it, and how the design survives the test of time." It added that its structure should highlight, again I quote, "the uniqueness of the bridge's geometry, materials, and space." End quote. The design criteria was driven by a pre-study of different bridge types permitted to be submitted for approval and, again I quote, "it has been determined that a truss or a hybrid of sorts was the best topology for the site given the budget, site constraints, and desired aesthetic level." End quote. The bridge consisted of a single span across the roadway of 174 feet, that's 53 meters, at a height of 18.5 feet, which is 5.5 meters above the roadway. First, a little bit about truss bridges. Truss is derived from the French word truce, circa 1200, which roughly translated means a collection of things bound together. In an engineering context, a truss is a structure that comprises of two force members where the members are organized such that the components collectively behave as a single object. Truss bridges are referred to in civil engineering circles as truss girders, lattice girders, or open web girders, but they all follow the same basic principles. Thinking about the side section view of a truss, particularly a planar truss, the top beams are called top chords, the bottom beams are called, well, just that, and the angled and vertical or horizontal connecting beams are often called webs. They aren't too complicated, but here's the concept. A bridge span of this type has two pivot points, one at each end, and the weight of the bridge, and anything on it or traveling over it, is distributed across those two pivot points. Turning moments describe how the further the mass is away from that pivot point, the more force is applied. Hence, the middle of the bridge will create the most force against the pivot points. Imagine the truss consists of a single triangle with a weight in the middle of the bottom beam, otherwise known as the deck. In a truss design, this would include a vertical web member that connects the center of the bottom beam with the top or apex of that triangle. Just ignore the fact this example has no top chords, it's not relevant for the example. The mass in the center of the deck creates a turning moment against both pivot points. The vertical web member is in tension as the mass pulls it downwards, but this is transferred equally between the two diagonal web members that join at the apex of the triangle to the pivot points. Those diagonal members therefore are in compression, and finally, the turning moments applied to the pivot points will attempt to pull the deck apart, which means the deck itself is also in tension. So to quickly review, the vertical member is in tension, the bottom beam is in tension, the diagonal web members are in compression. The beauty of the system, though, is that everything is designed to be in equal balance with the right combination of compression and tension in the design. At geometrically balanced angles in our truss, triangles, and boxes, we can cover large spans relatively efficiently. Of course, that's from a static loading perspective. Honestly, dynamic load is a whole nother layer of complexity, but suffice it to say, the key points in a truss design are: materials must meet tension and compression requirements per the design, angles between members and connection points must be balanced to properly distribute the forces and loads applied. Truss segments are also often combined with overhead cabling in suspension, with a traditional suspension bridge with a tower at each end of the span, or for a cable-stayed bridge with the support pylon positioned either centrally or multiple equally spaced along its length. This allows for much greater spans, with the truss segment providing stability between those cable stays. So let's talk about the incident itself. At approximately 9 a.m. local time on Thursday, the 15th of March 2018, the bridge construction crew were retensioning the post-tension rods in member 11 using a hydraulic jack in response to a directive provided by the bridge designers. At 1:46 and 43 seconds, the northern concrete truss member 12 blew out, rapidly fracturing and losing its structural integrity. Within 1 second, the node where truss member 10 connected with the deck split open and the entire deck started to fall. Within 2 seconds, the remainder of the truss segments lost their geometric stability in a domino effect, rippling from the failure point to the far side of the truss segment. The deck was no longer supported by the truss members, and it fell down onto the roadway, and partially or fully crushed 8 vehicles, 7 of which were occupied. The entire collapse was over in only 2 seconds. At 1:47 p.m., the Miami-Dade Police Department were called and they arrived on scene at approximately 1:52 p.m. The Sweetwater Police Department, Florida Highway Patrol, and Miami-Dade Fire Rescue were also dispatched, with most arriving within 10 minutes. 5 bridge workers and 5 members of the public were injured. 1 bridge worker and 5 vehicle occupants were killed. Mr. Navarro Brown, 37-year-old employee of Structural Technologies who was working on the restressing procedure on the bridge at the time of its collapse. Ms. Alexa Duran, 18-year-old, a student at the FIU. Mr. Oswald Gonzalez, 57 years old. Mr. Alberto Arias, 53 years old. Mr. Rolando Fraga Hernandez, 60 years old. And Mr. Brandon Brownfield, 39 years old. The entire collapse was captured on dashcam video mounted on a construction-related pickup truck that was approaching the bridge from the west, as well as from the FIU parking garage security camera. So what went wrong? The NTSB noted that the most probable cause in the FIU pedestrian bridge collapse was the load and capacity calculation errors made during design by FIG, specifically truss members 11 and 12, where they connected with the bridge's deck. It was designed to be a 2-span, single-plane concrete truss bridge with 2 spans and an approximately central vertical support pylon. It included a concrete deck and a concrete canopy connected by a single row of concrete diagonal and vertical support members which extended down the center of the bridge in a truss design. In an attempt to visually make the bridge look like a fully cable-stayed bridge, each diagonal truss member was designed to be a different angle and length, such that each truss diagonal member aligned with each of the steel pipe stays that connected to the upper pylon. This resulted in irregularly shaped diagonal truss members, each with different angles and lengths, which created different loads at each connecting point of the truss members. There were 12 members connecting the deck and top chords, numbered 1 from the south pier to 12 at the central pylon. The end members were vertical, as was member 5, but all others were at irregular angles. The concrete deck acted as the bottom chord of the truss, with both longitudinal and transverse post-tensioning. The concrete canopy acted as the top chord of the truss, with longitudinal post-tensioning. The diagonal truss members were aligned along the center line of the bridge. There was no second set of trusses in this design. The main span truss members 3, 5, 6, 7, 8, and 10 were permanently post-tensioned using internal post-tension rods. The other main span truss members 1, 4, 9, and 12 were not post-tensioned. During construction, as it needed to be done in stages, members 2 and 11 were temporarily post-tensioned. Finally, connection nodes along the top, called blisters, were the anchor points for the steel pipes. At the time of the collapse, the pylon support pipes had not yet been installed. Now, normally with a truss bridge, there are 2 trusses in parallel, with lateral cross bracing between them. This provides more lateral stability against swaying, but it also provides some redundancy. If one of the truss members is compromised on one side, then the other can take the load until it's repaired. Pre-stressed concrete is also different from normal reinforced concrete, such that the steel reinforcement isn't just laid flat, concrete poured, set and done. For pre-tensioned, instead, the steel is placed in tension, with usually a large flat anchor point on the extremities of the slab or the member, held in place by external supports. Concrete is then poured and set, and then those external supports are removed, which then transfers the tension to the concrete itself. For post-tensioned, ducts are set in the concrete, and once it has set, the reinforcing is threaded and tensioned after the concrete has reached sufficient strength. Either way, you get a pre-stressed concrete insofar as the concrete is under stress before you even put it into a building or a structure, and in this case, a truss bridge. So you might wonder, why on earth would you do that? Well, because concrete is stronger in compression, and by placing it in pre-compression, you can get away with less steel reinforcing for the same strength overall, and in relative terms, larger spans with greater load-bearing capacity than non-stressed concrete. It's all the rage these days. During construction, this is roughly the sequence. Cast the superstructure concrete, cure all placed concrete, post-tension the deck, canopy, and truss members, and that includes temporary post-tensioning of the truss members 2 and 11. The main span was cast above ground level and was supported by a temporary falsework. The falsework then supports the weight of the bridge while the concrete sets, after which it's removed. So now, beginning on the 24th of February 2018, the falsework was removed from the middle of the span towards the ends of the span, thus transferring the load to the temporary end supports. These temporary supports are called megashores in the business. Once the falsework had been completely removed, the bridge was effectively entirely self-supporting. So far, all of that work had been done in the casting yard, which is off-site, and then the bridge structure is relocated to the work site using an SPMT, that's a self-propelled modular transporter. On the 10th of March 2018, starting at 4:30 a.m. and using 2 SPMTs, Barnhart Crane and Rigging moved the main bridge span, which weighed 950 tons, into position on site, and they were done by 12:30 p.m. that same day. So let's talk a little bit about the cracking. Bolton Perez sent 3 reports in total to MCM documenting concrete cracking in the main span. Beyond this, employees of almost every company involved, which included the FIU, took personal photographs of some of the cracks as well. On the 13th of February 2018, Bolton Perez's first crack report number 1 to MCM read, "The members showing these small cracks are truss members that share the same blister in the canopy of the already stressed members number 2, stressed 30th January 2018, and number 11, stressed 29th January 2018. We believe this first stressing operation has temporarily created tension on members number 3 and number 10, thus creating cross-sectional cracks transferring the tension loads to the steel on these members. No other Truss members within span 1 show any cracks similar to these shown on members number 3 and number 10. The intent of the report is to inform design-build team of these cracks. It is the design-build responsibility to assess them and determine if these cracks were expected while tensioning and monitor them accordingly if deemed necessary." End quote. FIG responded to Bolton Perez's crack report as follows, and I quote, "FIG received the crack inspection report prepared by CEI on the 13th of February 2018. Subsequent to receiving the report, MCM sent us an email clarifying the location of the reported observations on February the 15th, 2018. FIG has reviewed the report and offers the following comments for your consideration. CEI's observations of the conditions of members 3 and 10 after stressing members 2 and 11 are temporary in nature. The current condition will change as soon as the stressing of the PT bars in members 3 and 10 is performed. The release of the canopy falsework will improve the state of stress in members 3 and 10. As mentioned in CEI's report, the observations regarding the current condition of members 3 and 10 are the results of an intermediate step in the stressing operation. It is recommended that the truss members not be marked with a marker or Sharpie, as this will lead to discoloration of the concrete." End quote. So they were expecting the concrete to uncrack itself later, apparently. Okay. On the 28th of February 2018, Bolton Perez submitted a second crack report to MCM, and I quote, "Please refer to the pictures attached regarding some cracks seen on truss members of span 1 after the removal of the formwork. Forward to the EOR, that's Engineer of Record, for their information. We will monitor these or any other developing cracks on the bridge, but we would like the EOR to provide a response and determine if these were expected during the bridge stressing. The one due to the size we believe needs special attention is the crack shown in photos 5, 6, and 7. End quote. On the 7th of March, FIG asked for more specific information as to where the photos were taken on the bridge components, and MCM responded the same day. With no response yet to their concerns, MCM sent a follow-up email on the 12th of March now with more cracks showing, stating, and I quote, "Following our previous emails regarding the noted cracks and as witnessed on site by FIG as part of the movement erection support, attached, please find photos depicting the cracks developed prior and post the span 1 erection and or distressing of the truss members 2 and 11. Your team may have most of these pictures. It is our opinion that some of these cracks are rather large and or of concern. Therefore, please review and comment as promptly as possible and advise if there is a required course of action to remedy or address these right away. Your immediate attention and response is required." End quote. On the 13th of March, FIG responded with the following, and I quote, "FIG is evaluating this situation as a top priority and will be making recommendations as a result of this evaluation. As of right now, we do not see this as a safety issue, but we do recommend that MCM place plastic shims," end quote, in various positions, in lots of detail. And then finally, I'll quote again, "FIG will be back in contact with MCM to give updates and recommendations from evaluations," end quote. There were a few emails sent that day, and at 5:18 p.m. another one, and I quote, "Please find the additional recommendations and requests below that FIG thinks will be beneficial for the structure. Again, we have evaluated this further and confirmed that this is not a safety issue," end quote. They then recommended reinstalling the post-tension bars in member 11, but not to member 2. Set a stressing force to be applied and reiterated, and I quote, "FIG recommends to stress these PT bars as soon as possible, but again, this is not a safety concern," end quote. So now we've arrived on the 15th of March, which is the date of the incident. At 8 a.m. in the morning, the FIG engineer of record observed the cracking firsthand on site. Whilst we're on that topic, the definition of an engineer of record, for those that are interested, from a Florida law definition site, engineer of record means the professional engineer registered and licensed in the state of Florida that prepared the engineering drawings and documents presented to the district for approval, or the professional engineer registered in the state of Florida that has accepted responsibility for the design of the engineering drawings. It's a common role for civil engineering projects in many parts of the world. And the EOR for FIG was William Pate. At 9 a.m. that morning, there was a meeting to discuss the situation with FIG, MCM, FDOT, Bolton Perez, and the FIU. Before actions or decisions could be made, less than 5 hours later, the bridge had collapsed. An interesting point about the re-stressing of member 11 was that the FIG EOR did not have the provided re-stress calculations peer-reviewed, as they were intended to bring the main span back into its pre-existing condition, as they said, in the casting yard to address the cracks that had formed. Therefore, they did not see it as a design change, and hence it did not require review. The FDOT specification for pedestrian bridges, section 10.3, states, any design calculations, details, or changes must be signed and sealed by a professional engineer licensed in the state of Florida. I'd like to take a minute to talk about the network and how you can help us out. The Engineered Network launched in 2015 and has several shows that take varying levels of time, effort, and research to prepare for, as well as to record, edit, and release to you, our listeners. Over time, the ways people could support the network have evolved. Initially, through sponsorship advertising, which we're trying to move away from, we're now moving to a listener-supported approach, and to that end, we've had a Patreon since 2015, and there are 6 support tiers, each with different benefits available to you. Basic supporters are for those who want to contribute something as a thank you for what we do here. It's our most popular support category. Named supporters and above get their name added to the Engineered Network homepage as a thank you. Premium and above levels are where it gets interesting. As a premium supporter, you'll get access to higher quality encoded audio files for all of our shows, ad-free and released before the public versions go live. Then we move to our producer levels, silver, gold, and platinum, all of which get a name mention in the episode audio itself and in the episode show notes. Gold and platinum producers are allowed to influence which topics the shows create, so you can have your own say in what we cover on the shows. Apple Podcasts now has the equivalent of our premium level in the Engineered Network channel subscription. All the same content that exists for premium and above patrons, but via the convenience of Apple Podcasts. Finally, we also support streaming value with Podcasting 2.0 enhancements. These allow you, the listener, to stream Satoshis, that's Bitcoin Lightning if you're into all that, and by using the right podcast client app, you can stream sats in real time as you listen and boost bonus value whenever you like. You're in complete control. So if you're a fan of any of our shows and you want to help us out and ensure episodes are continued to be made, now there's lots of options that you can choose from. And no matter how much, what level, or whatever way you like, know that it is all very much appreciated and it makes all the difference. Thank you. So what lessons did we learn from this? The NTSB listed 30 individual findings that go down to an extensive level of detail. Rather than discuss them all, I'd like to pick 3 categories, which each consist of several of those findings: traffic control, design errors, and QA during construction. Let's start with traffic control. When the re-stressing was underway, traffic had been stopped directly underneath the specific lanes where the work was occurring overhead, but not the others. However, it was a single span. So if something went wrong, the entire span could collapse, and it did. No one was thinking about that possibility, though, despite all of the cracks growing for weeks. As soon as the cracks were seen, they should have simply not sent it to site. But when it was installed on site, they should have closed the roadway underneath before determining the correct remediation action to take. The NTSB recommended changing the Florida bridge construction oversight procedures to emphasize the need for bridge and road closures to protect public safety when any structural cracking occurs, which is very sensible. As a side note, in Brisbane, Australia, where I've lived for 20 years now, in October 2006, the Ann Street and Alice Street on-ramps were closed shortly after a hairline crack was found in each of them. The worst was 2 meters long and 0.4 millimeters wide. After significant engineering review and load testing, they were reopened again several days later. The expressway includes the second busiest bridge in Australia, and in subsequent years, a pot bearing replacement program was put in place to address the underlying issue. The point is, though, at the first sign of a structural crack, the entire roadway was closed until it was deemed safe. The FIU bridge wasn't open yet to pedestrians, but the roadway underneath was open to vehicles. At the first sign of structural concerns, the roadway should have been closed. Remediation activity should not have been needed to trigger a closure. They should have just done it as soon as there was any doubt. Because as soon as there is any doubt, there is every doubt. Let's talk about the second thing. Let's talk about design errors. The NTSB had a somewhat blunt technical recommendation to the FIG engineers, and I'll quote it: "Train your staff on the proper use of the permanent net compressive force normal to the shear plane when calculating nominal interface shear resistance." End quote. In my line of work, that's like saying, don't forget what happens when you bundle multi-phase power conductors. So what did FIG get wrong for such a scathing judgment? In fact, what does that even mean, what they said? For those that aren't civil engineers, during the investigation, they found that there was a lack of design detail surrounding the bridge in its partially constructed stages. The detail in the design for the fully completed structure was actually quite good, whereas the design detail available for the main span without pylon support, as it was when it failed, was extremely light on detail. And due to this lack of detail at the failure configuration that the bridge was at, the NTSB were unable to determine specifically which errors into the model were truly incorrect, and the investigative team had to develop their own independent model to calculate what the design loads on the impact nodes would have been. To understand the next bit, we just have to quickly talk about cold joints. When you cast a new concrete element onto an existing concrete element, this interface between the two is called a cold joint. Cold joints are weaker than a continuously cast section, but the shear forces required to break a cold joint can be overcome by adding reinforcing between the two sections. You can rough up, as they say, the interfaces to make it an irregular interface rather than a smooth one. And post-tensioning can be reapplied afterwards to add additional compression. The main span of this bridge was built in 3 casting phases, and this resulted in cold joints at the end of every truss member, one at the bottom connection with the deck and one with the top chord or canopy. The team's calculations found that the nodes for members 1 and 2 and 11 and 12 were approximately 20% larger than they were measured in post-collapse check calculations. It was suggested that additional cold joint interface roughening of about a quarter of an inch, which is about 6 millimeters, would have improved the resistance of that joint to shear forces, but even with that, it still would have been unable to support the design loads. Worthy of note, there were no specific instructions provided by FIG specifying roughing up of each interface to the cold joints. Never mind. So how did FIG incorrectly use the permanent net compressive force in their load calculations? Well, ordinarily, the load factor that you'd apply would be a range to ensure you check both the maximum and minimum conditions, accounting for the dead load and the dynamic load. And the LRFD, which is the Load and Resistance Factor Design specification, states the importance of checking the low value very clearly. It says, and I quote, "The minimum value of the load factor for that permanent load shall also be investigated." End quote. The FHWA recommended a 0.90 load factor be applied for the minimum conditions against the dead load, which is the weight of the structural component of the bridge itself and any non-structural items that's attached to that bridge. The NTSB words this explanation quite well in their final report, so I'll quote it verbatim. A designer would then also artificially reduce, again through factoring, the capacity of the bridge, which would result in calculations showing that the design bridge would be able to hold up less weight than it really could. By making these adjustments together, heavier weight and lower ability to hold the weight in the design, the designer would have provided a safety margin for the actual bridge design, which is considered a factor of safety. By improperly using a load multiplying factor of 1.25 in the PC, permanent net compressive force calculation, FIG effectively increased and thereby overestimated the bridge's interface shear capacity by approximately 25%. End quote. Another oversight was the assumption about the redundancy factor. The NTSB concluded, and I quote, "FIG used poor judgment when it determined the bridge was a redundant structure and then erroneously used a redundancy factor of 1.00, which is commonly used for structures with redundant load paths." End quote. There were other errors, but these were 2 of the bigger ones. Finally, let's talk about the design check. When we design something, we always need to get our design checked. Everyone is human and humans make mistakes. This is a well understood thing. Not only that, history has shown that an organization, due to its structure, its rules, training, or lack of training, can have their own blind spots when it comes to design and design review. Hence, we expect both an internal design review within the design organization as well as an external design review by an independent third party. The higher the risk of the project, the more important the third-party review is. So if we accept that errors are inevitable at some point, then we also accept that a detailed third-party review is required at some point as well. From a legal perspective, though, the FDOT Plans Preparation Manual at that time classed the pedestrian bridge as a Category 2 structure, and that would require an independent peer review. The reason it was a Category 2 was concepts, components, details, and construction techniques with a history of less than 5 years of use in Florida, for which this bridge had all of those things. A peer review firm must, and I quote, have no other involvement with the project and be pre-qualified in accordance with the Florida Administrative Code Rule 14-74, end quote. It also states, the peer review is intended to be a comprehensive, thorough, independent verification of the original work. An independent peer review is not simply a check of the EOR's plans and calculations, it is an independent verification of the design, end quote. During the design, Lewis Berger were given the subcontract for the design review. However, it was specifically and only for the final design of the bridge in its entirety. In response to the NTSB following the incident, the engineer from Lewis Berger stated that, and I quote, "My model was for the structure as one structure. Doing construction sequence staging analysis was not part of our scope, and again, doing such an analysis requires much more time than what we agreed." End quote. In other words, construction sequencing analyses were not performed despite there being both FDOT and FHWA requirements to check constructability considerations of the bridge by AASHTO LRFD Section 2.5.3 and by FDOT Structures Design Guidelines Sections 2.13, 4.58, 4.59, and 6.10. And both the LRFD and FDOT's guidelines were required in Lewis Berger's scope of work, and hence modeling and design verification of the structure in parts during various stages of construction was also required as well as the whole structure. Unfortunately, the whole structure was all they did. And not only that, there was confusion surrounding the requirements for peer review submissions. With most designs reviewed at multiple stages of delivery, the only review done by Lewis Berger was done of the 90% design, but they never submitted it. It was held over for the 100% design completion, which hadn't taken place before the bridge collapsed. A quick aside about how we got to this point with the peer review, though. In early 2016, MCM engaged FIG to act as both the engineer of record for the bridge and engineering services for the project, and FIG had written in their technical proposal that they would perform the design check internally, not via a third party. On the 30th of June 2016, the FDOT informed FIG that internal peer review was not compliant with legal requirements and they needed to nominate a third-party peer reviewer at their expense. Well, FIG hadn't budgeted on a third-party review, but they went out for 3 bids with the full scope of work that included a full peer review in accordance with FDOT's Plans Preparation Manual. And they had 3 respondents, weighing in at $63,000, $85,000, and $110,000, which was Lewis Berger's initial submission. In early August, there was an email exchange between Lewis Berger and FIG, whereby the quotation was revised down from $110,000 to only $61,000. That's $2,000 less than their previous lowest quote. And the scope, though, remained unchanged. Also, they reduced the time they'd say it would take by 3 weeks, and that then would align with the project schedule. So the short story is Lewis Berger slashed their price almost in half and shaved a big chunk off their delivery time in order to win the job. And then they decided to only perform an analysis of the full structure and submit it at final completion to save money. And FIG didn't call them out on it when they really should have. Finally, there was an issue with Lewis Berger's registration. FDOT records indicated that Lewis Berger Group Incorporated had applied for work type 4.3.1 in 2013, but the application wasn't approved due to the applicant having insufficient engineers with the required experience for this work type. A technical error had mistakenly listed Lewis Berger as pre-qualified for work type 4.3.1 complex bridge design concrete. In Lewis Berger's correspondence with FIG engineers, they stated that they were pre-qualified, However, as they were unable to provide any evidence beyond the website listing their pre-qualification for this bridge type. The NTSB ultimately recommended to FIG engineers that they, and I quote, institute a company policy to obtain a pre-qualification letter before finalizing any peer review contract with any engineering firm or company being considered to conduct peer review services, end quote. Pretty straightforward. Finally, the QA during construction. As discussed previously, there were formal notifications sent to the bridge designers during the construction of the span, both before it was moved to site and when it was installed on site. As soon as the formwork was removed, the cracking started at the badly designed nodes, and including the one that actually failed on the day. It was brought to the attention of the bridge designer, but they dismissed it as not being a safety issue. That's not excusable. A civil engineer with several years of experience should be able to identify just by visual inspection if cracks are structural or non-structural in nature. In general, structural cracks are cracks that extend deeper than half an inch, 12 millimeters. And if there's any uncertainty, then they can just order an NDT, that's a non-destructive test, maybe an ultrasonic pulse velocity or an impact echo test, just to confirm how bad the cracks are. Of course, both of those take time and cost money, but it's not a game. You're playing with people's lives, so you should get it right. On the 28th of October 2019, Vice Chairman Bruce Landsberg filed a damning concurring statement listed in the NTSB report where he stated, and I quote, "The checks and balances that were required and incumbent upon Lewis Berger were completely lacking. Lewis Berger lowered their bid to review the project by 43% in order to get the business, but also reduced the scope of their review. The reason given was there wasn't enough money in the project to cover their efforts. That's both disingenuous and unconscionable." End quote. And I completely agree with that. Let's talk about the fallout. MCM were already $8 million US in debt when construction began, and the losses from the incident led to MCM filing for bankruptcy in May 2019. MCM had brought claims on their 4 insurance companies to cover the $54 million in damages. In September of 2020, MCM agreed a settlement of $9.5 million also with the FIU and filed their own lawsuit against WSP, which actually stands for Williams Sale Partnership, originating in 1969 in England, but no one calls them that, it's just WSP. And if that sounds odd, WSP, who weren't directly involved in the project, they acquired Lewis Berger Group in a deal worth $400 million US in December of 2018 after the incident. Hence, in its lawsuit, MCM states that WSP is still liable, even though the acquisition was completed after the incident occurred. On the 14th of July 2020, the FHWA temporarily suspended FIG Bridge engineers and Mr. William Pate, the engineer of record for the job, from working on federally funded projects for a decade. Whenever engineering failures take innocent lives, it's especially hard. These weren't the risks that they signed up for. 5 of the victims were just sitting in their cars, waiting for the red light to turn green, to carry on with the rest of their day. They had no time to react, no time to move, no time to escape. They had no chance. Ms. Duran was giving her friend a lift to the doctor. Oswald and Alberto were heading to the travel agent to pick up some plane tickets. The bridge was non-standard, and whilst it's not impossible to build a bridge like this, it requires very experienced engineers and solid peer reviewers to ensure that it's done correctly. There's a reason, a good reason, that truss bridges generally don't look like this one tried to look. Clearly, FIG didn't understand the pre-qualification requirements, and Lewis Berger, either they didn't understand their legal requirements for peer review, or they chose to stick with the line, "We weren't paid enough to do it, so we're not doing it." But either way, it wasn't done properly. When you're building a structure, the final load calcs are only part of the story. You have to look at the progressive loads as it's being constructed as well. You don't go from one span to all done by snapping your fingers. It's all of the steps in between. You need to account for all of them in your design and in your design checks. In this case, a thorough design check of that span in isolation would have found the problems. The denial when the cracks were found and the failure to stop the job by the prime contractor were just bizarre and exasperating. I worry sometimes that this drive by idealistic people with money, They want their building to look different to all the others. They want their bridges to be special, unique, themed, or something that stands out. When those factors drive form over function, it's always a more difficult path. And if you engage the wrong people to do the job, it quickly becomes the most dangerous path. They could have built a boring truss bridge, and it would have been fine, probably. At the time of recording, this happened about 3 years ago. Now, you'd think, surely, with the best computer modeling software available in history, professional engineers involved, and hundreds of years in building bridges in the United States alone, and it still failed. You might be surprised in engineering, even professional engineers make mistakes. People are under time and cost pressures. Sometimes their companies overcommit to work and they're stretched far too thin. There's a long list of reasons why, not to mention non-work related stress and distractions. And that's why design review is so critical. You know why other engineering design areas don't end up looking like this bridge did in the end? It's because a good peer review caught it before it was too late. A concerned construction supervisor stopped the job at the first sign of the very first crack. This incident occurred because the people involved didn't do those things. They pressed ahead anyway, and it was the wrong call. If you're enjoying Causality and want to support the show, you can by becoming a premium supporter. We're edging closer to our monthly goal to go advertising free across the network, but we can only do that with your help. You can find details at engineered.network/causality about how you can help this show to continue to be made. A big thank you to all of our supporters. A special thank you to our silver producers, Mitch Bilger, John Whitlow, Kevin Kosh, Oliver Steele, Leslie Law Chan, Hafthor, Shane O'Neill, and Bill. And an extra special thank you to both of our gold producers, Stephen Bridle and our producer known only as R. Causality is heavily researched, and links to all materials used for the creation of this episode are contained in the show notes. You can find them in the text of the episode description of your podcast player or on our website. Causality is a podcasting 2.0 enhanced show, and with the right podcast player, you'll have episode locations, enhanced chapters, and real-time subtitles on selected episodes. There's details on how in the show notes. You can follow me on the Fediverse at Chidgey at engineered.space, on Twitter at John Chidgey, all one word, or the network at engineered_net. This was Causality. I'm John Chidgey. Thank you so much for listening.